So I graded the homework last night. Okay, so there were a few people, I mean, in the minute before obviously starting, but a few points. So I graded the problem with inverse permutation matrices is transpose. So a lot of people would write something like, like a permutation matrix is something like ER, which is fine. But then they would go through some kind of long argument to use this to say that transpose was the inverse. A few people did it well, but the thing is I need to know what these are, right? So if you're making an argument like that, you've got to tell me what these elementary matrices are. Not just, you don't have to be so specific that you say, okay, well, they are this matrix, but you should say, okay, this is a matrix from a transposition. Because otherwise I don't know why transpose is the inverse of those. I take an elementary matrix and take its transpose, it's not the inverse in general, right? There are three different types of elementary matrices. So I guess what I'm asking of you guys is to be a little more detailed about what you're putting into your argument so that I can say, okay, they know why that's true. So that was one comment. Another comment was I did see with permutations, a lot of people, about half the class really, still maybe doing the wrong order. So if I take the product of these two permutations, right? The way I want to take the product is what you do is you imagine these as two functions. Each transposition is a function. Maybe I should put a recycle or something in. Imagine these as two functions. And then you're going to put in some number here. And this is the first permutation to act on it. And after you've acted on that number with this permutation, you act on that, whatever you get with the next permutation. The first and the second. And of course, if you have more, you can keep on going to the left. I think it's because I'm left. So let's look at an example. So let's say I want to know where 1 goes. So I'll put in 1 here. And the first permutation tells me that 1 goes to 3, right? 1 goes to 3. The second permutation says 3, nothing happens to 3 here. So that means 1 goes to 3. Now I'll ask where 3 goes. And I look at the first one, 3 goes to 2. The second permutation tells me that that thing I got 2 goes to 1. That's telling me that this is cycle. You can ask, where does 2 go? Well, 2 is going to be sent to 1, and then 1 is sent to 2. So it goes forward. The key point is I did see people doing it in the opposite order, where they would test this first and then do that. That's not correct. All right, just some comments on the homework. Again, we'll have at 3:30 today in my office. If you want to come, it's fine. If you want to join by Zoom, that's fine. It's the same link as last week. I'll do some problems for this week's homework if I get requests for them. I think people would benefit. I mean, judging from grading, I think people would benefit from seeing some things worked out. So it'd be great if people just let me know if there's certain problems they want to look at. All right. I'm going to try and slow down a little bit, but I can't slow down too much because I want to get some fun stuff. So,
Doctor,
yeah.
What was your office number for that?
Yeah. My office is Cardwell 215. Today's at 3:30. If people have somehow the Zoom link, it's not there to you, I can resend it. Would people like me to make another announcement in Canvas for the Zoom link, or do people have it? Okay. It's okay. Okay. Or yes, you want me to send it? Or yes, you have it. Okay. Thank you. All right. Okay, so last time we talked about subgroups, and we did a nice theorem about subgroups of the additive group of integers, right? We showed that all of those subgroups look like Z times A. And this time, I think I will start with a proposition about these. So all subgroups of groups, additive group are other types ZA. So in the theorem, it says either it's the trivial group or it's ZA, but actually if you take A to be 0, that's still ZA. 0, the trivial group is ZA, Z times 0, but 0 is not possible. So, because you could say non-negative. All right, so let's take a look here. Okay, so I wanted to look at this proposition, give us a little sense of why the greatest common divisor is something we can understand just from understanding subgroups. So, okay. That's not what I want to do. All right, so you'll recall, and in fact, this is sort of, maybe I'll give a general definition. If, let's say, A and B are subsets, really, of an additive group, G with some addition, or H and K are multiplicative subgroups of some G with the law of compositions written as multiplication, you're right. These are subsets, sorry, right? You know, A plus B for the set of all the sums. A, B. I will say that when one thing, it's very common, you would never use an addition as like the symbol for your composition. Well, maybe that's not true. In math, you would very rarely use addition if your operation was not commutative. I guess with concatenation they do that, but strings. But usually, if we're dealing with non-commutative things, we use what they call. But it's the same kind of notation. H is an H. The difference, of course, well, maybe not, of course. The difference is that if these were subgroups here, and this were an abelian group, then this would be a subgroup. If you have two subgroups and G is non-abelian, this is not necessarily a subgroup. And we'll see instances of that. Anyway, we're going to use this notation here for this proposition. So one thing you can see, I think, is that if you look at the property B, B is saying that D is the greatest common divisor of A and B. i.e., D is equal to the greatest common divisor. Right? It's a divisor that any other thing that divides A and B must divide. It's the biggest. Let's try to prove this together, see how far we get. So actually, before I prove this, let's just make an observation first. It's a notational observation. And maybe I want some silly letters. Let's say R and S. R is an ZS. Oh, yeah. What can you say about R? Yes. Another way. So if you walked over to an elementary school to pick on some kids, right? And right, as you all do, I know very regularly. And you went and you put something like this, put some notation like that in front of them, you know, and said, hey, what does this mean? They would say, what are you talking about? Leave me alone. You know, but now, you did the same thing, you probably still need trouble, but they would understand what you're saying. So what, can you translate this for someone in elementary school? That I have two integers or two whole numbers if you want, R and S. What is this saying about them? Yeah.
R is a multiple of S?
R is a multiple of S, or S divides R, right? S divides R. So there's notation for that, which I'll try not to use, but it's just, have people seen this notation? No? Okay. That's notation. It just means S divides or if you want R.
It's the same S and R from part C.
No, this is just, I'm trying to use, no, very much not. Sorry, I was trying to use something that I saw D, A, and E and all that, and I didn't see R and S. This is just a complete independent observation, but we want to use it. So we want to prove A. We want to prove that B divides A and B divides B. Well, we have a way of writing that now in terms of our subgroups, right? Instead of writing, well, we'll say D divides A and B, if and only if D is an element, A is an element of Z times D, and B is an element of Z times D. Okay, now, what are our assumptions? What are our assumptions here in the proposition? Well, we have two integers. They're not both 0. D is their greatest common divisor, okay, which we'll see means this. But the way that Arden defines it is this. That's so Z of D is A equal to Z of A plus Z of B. So we're given this. So we know that D is an element of ZA. Pardon me. I'm sorry. We know that A is an element of ZA plus ZB, right? Can someone tell me why? Okay. No, hold on. We don't know it's an element of Z. We just said this divides A and B if and only if this happens. So the phrase here is, we want to prove this. That's true if and only if this is true. So we don't know this. We want to prove it. So what we're doing is saying, hey, rather than talking about this, let's try to prove this. Now, what we do know, though, is that A is in this. So why is that true?
Because it's already an element of ZA.
And so can you write it as something in, so it's an element of ZA, so it's A plus what it be?
The identity.
The additive identity, 0. Right? Maybe I'll write that rather than, so A is equal to A plus 0, which is in here. But now we do know, what we are given is that ZD is equal to this. And equivalently, B element, or sorry, B is equal to 0 plus 0 plus B, which is an element of ZA, which we are given is equal to ZD. So it's D divides it. The argument kind of clear. I'm sorry, I probably didn't present it in the best way there, but is it clear? The one that I have seen this a couple of times in Homomorphisms, and I try to write the comment. So do read the comments. There are cases where people are assuming what they're trying to prove. That leads to circular logic. And that is a big no-no if you're giving a proof. So it pains me, but I still give partial credit. Really be careful about that. Yeah. Question.
So, and I think I'm off base, but I can need an explanation why.
Uh-huh.
So I'm looking at it, and that S group or that ZD group we defined seems like it's not a group because it doesn't seem closed under composition. Like, let's say A was 2 and B was 3. If it's closed under composition, 2 plus 3 equals 5 has got to be in the group, but like 5 doesn't seem like it's in that group.
Well, okay, A is 2 and B is 3. What is D?
Oh, 1. Oh.
The loneliest number.
Why?
No, it's okay. It's okay. It's good to explore. No, I want to encourage that kind of like experimentation with these ideas because, you know, it does take a second. It's like, wait a minute, what is this? Why is, because yeah. So, and that indeed is sort of, that's this Bézout theorem telling you that in fact you can get the greatest common divisor as sort of a linear combination of A and B, an integer linear combination. All right. So for B, okay, so now, so let's suppose that an integer E divides A and B. Well, then A is an element of ZE and B an element of ZE. Okay, but since Z of D is equal to ZA plus ZB, we have a D is equal to something times A. I don't know. I don't want to do this, but maybe this is part C, a proof of part C as well, which is just obvious, I think. R times A plus S times B. Right, Z times ZA is the set of all elements that look like a multiple of A. So this is sort of the definition of saying well, saying D is in here is saying that D is of this form, right? So we have C. C is not, I'm not going to prove that separately. So we have this, but now we know that A is in ZE, so R times A must be in Z. Because that's just E plus itself R times, if you have a negative. So both of these are, and likewise, S times B is also in ZE. So both of them are in ZE. It's closed under addition. So is their sum. Thus, again, using our observation, E divides. In other words, all we needed to do is show that D is in this group. All right, so that's how some of these proofs go. Again, a very important corollary that is used frequently in algebra and number theory and all, even in, I would say, to some extent, even in like the reason partial fractions work. To some degree, when you're doing calculus, follows from this kind of a theorem, which is, you know, if you have the greatest common divisor of two integers is 1, then there are integers R&S such that this is just this C, part C of the last. Thing. I think this is called Bézout's theorem. Maybe it's for a different kind of ring, a different kind of algebraic structure. But it's used. Okay. So I'll let you, there's still some other things in this section, but I'm going to let people sort of work on that independently, read through that. On the least common multiple, things of that type. I think this proposition is pretty good to have at our fingertips, but I want to move on and quickly talk about the next section, which deals with something called cyclic groups. So what is a cyclic group? Yeah, sorry, please. What did you need?
This corollary.
Yes, corollary. So it's just part C. Thank you for asking. It's just part C where D is 1. So we have this language. Two integers have greatest common divisor 1. We call them relatively prime. They have no common prime divisors. And it's kind of funky. So how does it work? Like, how can you find R and S? Well, there's something called a Euclidean algorithm, which is essentially kind of a version of the division algorithm that you can go through to actually calculate R and S in this. It's sort of a recursive algorithm where you get lower values. We're back out to here. But I'm not so concerned with that. If you would like, you can see Euclidean algorithm. But it's sort of this, there was this question, like about 2 and 3. Well, 2 and 3 don't have any common divisors. And of course, I can take, -2 plus 3 and I'll get 1. So here the coefficients are really simple, right? But, if I took 7 and, I don't know, 200 or something, I don't know, probably either, but you may have to work on it for a minute. I think the hard part is when they're both sort of large and they're separated by a median level, like I don't know how the complexity of the Euclidean algorithm, when it's hard, when it's easy. But you can always do it. That falls from this proposition. And the reason it's partial fractions is, well, I don't know if we'll talk about principal ideal domains, but there are other rings that are very much like the integers. One of them is like polynomials, one variable. Polynomials and one variable act a lot like the integers act. They're both these principal ideal domains. And there's a theorem like this for those. And then your kind of irreducible, your primes, your relatively primes may be like 2 linear polynomials. And so then the fact that you can do this tells you that if you have like a denominator and a fraction, you can kind of split it up into a sum of fractions. Partial fractions. Anyway, just trickery. Cyclic groups. So definition. So I'm just going to I'm going to give a slightly different definition than Arden, but a group is cyclic. G. I'll write it multiplicatively. Cyclic. If there exists element X, G, such that all other elements Y, G are of the form Y equals X to the N for some integer N. So you're allowed to have N be 0, in which case you define X to the 0 to be the identity. You're allowed to have that. And you're allowed for N to be negative, in which you're taking powers of the inverse, or you're multiplying the inverse by itself. So in this case, we say, we write one way we can write it. You don't have to write it this way. If this is the notation argues, common notation. Say X generates maybe I'll underline definition. Cyclic generator sort of notation. All right. So examples. So this is written multiplicatively, but this is, whatever your notation is, you can use additive notation, then you just have to replace x to the n by n times x. You're taking the operation n times. The one example with the addition. What is a generator for z? With addition. One is a generator, right? If I use the operation on one with the operation of addition, with just one, I'll get everything else. 1 plus 1, 2, 1 plus 1 plus 1 is 3. And again, remember, I'm allowed to take negatives or inverses, so -1, so on. And I'm allowed to take 0, so 0 times 1. So here we get generated by 1. But also, we could have taken generator -1. -1 would have been. Another example. I'm talking about 1 and -1. Take multiplication of 1 and -1. Take these two numbers, multiply them by each other. They're certainly closed, right? -1 is its own inverse. If I square it, I get 1. Group 2 elements. Finite order, order 2 group. Generated by -1. We have the notion of order of a group. Here, this is infinite. Here, this is order 2, meaning this is the number of elements in the group. Give you a third group. May or may not love. You'll love it someday. Multiplication. This is a subset, a subgroup, really, of complex numbers. It's an order 3 group, and it's cyclic. You can take x here to be the generator, or you can take the other one, the other non-identity. What is this group? What does this look like?
120-degree rotation.
Yeah, 120-degree rotations of the circle. I take my circle, give myself 3 elements. These 3 elements multiply in a closed fashion. If I square this guy, it goes to here. So in other words, I take this times itself, it goes here. I square again, I go here. I go back to the identity. As I said, this is a 120-degree rotation. Saying rotate by 120 and rotate by 120 again. If I rotate again, I set the identity.
That was generated by again?
It's generated by either one. It's a good question, right? It's generated by, so it's not generated by 1. 1 is not going to generate because 1 times 1 is 1. So I'm not going to get everything by taking products of 1. But I can take either one of these. And indeed, this is the complex conjugate of the first. So either one generates. You can do, these are called the third roots of unity. So there's the solution. You all know that there's a solution to this equation, 1. But there are 2 other solutions in the complex plane, and these are the other 2. You can generally look at all the solutions to this equation in the complex plane. You'll get n solutions, distinct solutions. Those form a group. That's denoted mu sub n, called the nth roots of unity. Complex plane is just awesome. I'm telling you guys. I'm telling you. Now, the good thing about cyclic groups, questions? The good thing about cyclic groups is they're easy. They're really easy, okay? They only kind of come in these two flavors, right? They're either infinite, in which case they basically are like this group. And we'll get a very concrete notion of what basically like means. We'll call them isomorphic. And then if they're not infinite, they're finite. And they're going to be sort of, well, they're always going to look essentially like this. There's going to be a generator, and then you're going to take the power and take the power, and let's say it's order n. Once you get to n, you'll hit the identity. So this is I'm just going to write this as a theorem. This is like proposition 2.42, but I'd rather just kind of explain it to you. So suppose X is a finite cyclic group, G here, cyclic group of order n. Then we can actually write down what G looks like, as I was just saying. We'll have some identity. We always have an identity. We'll have our generator X, and then we'll just start taking powers. And we know it's finite, so we know at some point it's going to stop, or at least it's going to start cycling around. It can't just be distinct elements forever. And the place where it stops, because we know X is a generator, is at the n minus first power of X. If we went one more, then we would get 1. So I'll say, and let's say we have some element A, it's equal to Qn, let's say, and then I divide A by n, and I get remainder R. Then, oops, n, sorry. And X to the A is equal to X to its remainder. This gives you a way of multiplying. So let's say that, see the proof. Well, what we know is that at some point, X to some power is going to be 1, right? You know, at some point, X to some power is going to be 1. We know. Why do we know that? Someone can tell me. Some power, call it M. Yes.
Because we know the order of the group.
Well, we know it's finite. That's true. And indeed, in a finite group, we know that, I'm not even saying what M is for now. I'm just saying that there's some number. Some number. I'm not saying it's N. Some integer. Yeah.
If there was no way to get back to 1, it would be an infinite group.
What if I went x squared, x cubed, x to the 4th, x squared, x cubed, x to the 4th? What if it like started looping in some weird way? Why can't it do that? Why not? Who says it? Well, let's say this. I'll say what you just said. So since G is finite, and all elements look like are of the form X to some power. I'm going to need it. Let's say R. At some point, we have to repeat. We have X to the R will equal X to the S for some R not equal to X. other words, we know after n steps, once we get to x to the n, once we get to x to the n, we've already, if we have n distinct elements, 1 to x to the n minus 1, x to the n must equal something in there. Right? But now we can just use one of the properties of the group. But groups have what? Besides being associative and having identity, they have inverses. So we can multiply, or we can think of cancellation if we want. We can multiply by the inverse. Let's say I said R is let's say R is less than S. If they're not equal, one is less than the other. 1 equals x to the s minus r. We know that there's some number after which x to the s minus r is equal. So now I'm going to say, if we know that, and let's call that number m. So we're calling this number m. This is the argument to show that there is such an m. So, I'm sorry, let me say for some smallest number. Smallest. So we want to, we of course, if x to the m equals 1, x to the 2m will equal 1 as well. But we want to take let's take the smallest possible integer for which this is true. So now I claim that with n replaced with m, we will get that indeed this holds. So if, let's say a is any integer, and divide by m. Again, we use this division algorithm. A equals, just elementary school division. We have a quotient m plus a remainder r. Now r is less than m and greater than or equal to 0. So we know we have this equality here. So now let's look at x to the a. A could be -2, and this still holds. So x to the a is going to equal x to the qm plus r, which equals x to the m to the q times x to the r. X to the m is 1, so this is equal to x to the r. So this gives us this equality for m. Now, why is this good? So we're almost done. What have we left out? Well, we want m to be n. We want m to be n, the order of the group. But now, with this in hand, we can list all the elements of G. So since G is generated by X, we have that G is equal to, well, a 1, x squared, and then we know once we get x to the m, we're back at 1. And we know that if there's a is any integer that's not in this list of 1, 2, all the way to m minus 1, we can think of this here as x to the 0. If a is any integer that's not in this list of exponents, then by dividing by m, we'll get it to be equal to one of these guys. So this list is an exhaustive list of all the elements in G. But we know the order of G is n, and this has m elements. Because order of G is n. So that tells us that this list is complete. This goes up to n minus. That's it. So all our cyclic groups are very comprehensible. They just look like this. Another way, for those that are in computer science, another notation that we'll have for a cyclic group, and again, we'll say they are isomorphic once we get there, is we'll show, well, this kind of shows it almost automatically, that this is essentially the same group as what's known as Z mod n. That's the mathematical notation that well, it's still, the jury is out here. Nobody knows. Some people write this, but those people. Huh?
I think you actually wrote out like Z and D.
Yeah, that's okay too. So that's like first brush notation. This is what's in many undergraduate and some graduate textbooks. But then if you go to like Math Overflow, where a bunch of mathematicians, you know, are free to express themselves, let's say, which I'm sure you don't want to go to, you'll see that this is, I think, preferred. I think the majority, not consensus, majority prefer this. That's because this has another, if you put a prime in for n, Z mod p, this denotes something called the p-adic integers, which is very different. That's sort of stuff you can't change that. So anyway, this is not something you guys need to worry about.
So which one's preferred for this class?
I'm going to be using this. Okay. I won't use this. But you'll see it in probably most of the other classes. If you take more math. I know all of you do. All right. So this is the idea behind cyclic groups. Now, what mathematicians do, and what scientists do, but I think what any good, intellectual person does when they think about a thing, is they do not take that thing and understand it in isolation. That is what, deranged people do, that are like on drugs or something. Like, that's a problem. Like you can't, you get obsessed with something. That's not, okay, we all have that problem, but, maybe not with me. What we want to do is want to take something that we're interested in, and we want to view it in relative to other things that are like it. So I don't want to take what we just did with groups. Right here, we took a finite cyclic group and we understood it as a finite cyclic group, and we classified that finite cyclic group. But what I really want to do is say, how do I relate two groups? How are they related to each other? How do they interact with each other? What can I learn from one group by knowing about another? So on and so forth. It's like you want to be like a social group person. So to do that, we need a sense of how groups are related. So that's the next section, and we'll just talk a little bit about it. But it's the beginning of a whole, like all good areas of mathematics have this feature. Topology, algebra, analysis, even like all of these subjects, you relate different structures that have some things you're interested in studying. Group theory is no different. We need to define, I think it's 2.5, homomorphisms. Similar shapes, Greek, similar shapes. But what are they really? What is the mathematical definition? So let's define it. Suppose we have two groups, G, G prime. I want to relate them. How do you relate two sets? You define a function from one set to the other. That's a way of saying I've got an element in set one, I can send it to an element in set two, that kind of forms some sort of bond. Those G and G prime are groups. Homomorphism. Function. say F. Now let's use V. V, G, prime. A function is just a function. It doesn't do anything. We want these things to relate these to algebraic structures. Which means this function should be compatible in some way with these laws of compositions for the respective groups. And the way we condense that, or the way we express that, is we say, okay, this function has to satisfy a single identity. If I take a product in group G, two elements in G and I combine them, and then I take phi and I see where it sends it, that's going to go to the product of their images. All two elements, any two elements. Do a quick example. We'll talk more about isomorphisms later, but I'm going to give the first simple example. Let's look at S2. We know this is functions from two types, two permutations on two letters. Let's look at G equals bijections on set AB. With composition. Tell me about G and tell me about S2. So S2 is not much, right? Permutations on 1, 2, right? So either it sends 1 to 1 and 2 to 2, or it switches them. How do people feel? It's not a complicated group, right? If I transpose twice, I get the identity. This is an order 2 group. What about bijections on a set AB? What do you guys think of it? Okay. Okay. Same thing, right? I just called 1A and 2B. It's the same thing. They're the same thing, but they're not the same, right? They're not exactly the same. One is a function on the set AB, the other is a function on the set 1, 2. They're different, but they're behaving the exact same way. So we can do something, right? In fact, we can look at this as 1, let's call it 1 tilde or something, and AB. So we can send this, go S2 to G, just send 1 to 1 R and 1, 2 to AB. This is a homomorphism. It respects the algebra structure. In fact, this is what's known as an isomorphism. Because it's got an inverse that says that these are essentially the same group. They just have different labels. They're called different things. What about this group? I just talked about a second ago. 1 minus 1 out of R, say, with multiplication. Think about that group. If I take -1 and I square it, what do I get? 1. So -1 squared is 1. 1 times -1 is -1. The product structure is basically the same as this. If I take this permutation 1, 2 and I square it, I get the identity. If I take 1 times it, I get 1, 2. It's the same idea. There's also an isomorphism here. We want to be able to say, okay, hey, these two groups, yeah, they look different, but they really have the same essential structure. The algebras really behave exactly the same. They just have different labels on their elements. That's why one of the reasons why we're interested in homomorphisms and isomorphisms is to relate these differences. But of course, they're not all like isomorphisms. We have another homomorphism that we've already dealt with. And in fact, you deal with homomorphisms all the time when you're dealing with calculus. You can write certain linear differential equations. But For example, you can take determinant, taking GL and R, n by n matrices with entries in the reals, and map it to R with the product, right? And remember, this is the set R minus the or minus 0. So this is the product on the real numbers, but you leave out 0. And why do we know this is a determinant? Why do we know this is a homomorphism of groups? You guys remember this? That expression is precisely the statement, this function is a homomorphism. So we can relate our group of invertible matrices to a commutative group, the abelian group of just real numbers of multiplication. That's a very useful thing. So we'll go through a bunch more examples on Monday. If there are some questions, please do read through it. This section is kind of has some length to it. New ideas, and we'll get to them Monday. Right. So
a couple of questions about that one.
Yeah.
So first of all, these homomorphisms don't have to have a correspondence.
Not at all. Not at all. They're not one. They don't have to be surjective.
And the next question is like, so these are permutations. Like these figures are permutations. What is this?
So they're also permutations, but it's not on a set 1, 2. Set 8.
Oh. Okay.
It's the same.
And then one would just send
A to A, B to B.
Okay.
So my point is that they are really almost identical, but they're not identical.
They're so close to identical, I couldn't figure out right.
How are they different?
1, -1.
There is a homomorphism to it. So it's a group. So I'm just saying, if I take that under multiplication, that's a group. And I'm just saying there's a homomorphism, which takes, I didn't write it out, but takes one identity, say, permutation to 1, and this transposition goes to negative. And you can see, now let's say call this phi. I take phi 1, 2 times 1, 2. Well, we know that this is phi of the identity. 1, 2 times 1, 2. 1. But we also know that this is also equal to like -1 times -1, right? Negative 1 squared, which is phi of 1, 2. That's basically the identity we need for a homomorphism.
So why are there permutations to give negative?
This is occurring inside of the set 1 minus 1. These permutations are in the domain of the function. They're occurring in S2. Okay. So we're multiplying those in S2 and we're putting them into our function, which lands in here. So it's two different worlds that we're connecting.
So 1, is included in the group S2, and it is a homomorphism within there.
Identity is it's in. So this is in S2, and then these guys are in 1 minus 1. And if you look at each thing I'm doing, I'm in the right spot. So here I'm in S2, and then I put it into phi and go over here. Here I'm in S2, I put it into phi, I go over here. But now I've applied phi, and I'm in 1, -1. So here I'm writing -1 times -1 in 1, -1. And here I'm saying I'm still in 1, -1, but now I'm taking the image of 1, 2. I'm taking the image of 1, 2, which is -1.
Okay, and that satisfies that.
Yeah. Okay. This is just an example of that property of homomorphism being satisfied.
Okay. So can groups be homomorphic, or is it just things like subsets?
You would rarely call two groups homomorphic. And the reason is there's always what's known as the trivial homomorphism. You can take every single element of a group and send it to the identity of another group. That will always be a homomorphism. So you wouldn't normally say these two groups are homomorphic. You will say that they're isomorphic if there's sort of a homomorphism going one way and back that gives you that are inverse to each other as functions. So we'll get to that. But yeah, I think isomorphisms are sort of easier to understand than homomorphisms.
Yeah, I'm trying to wrap my head around.
No, it's good. I'm glad you're trying to do that. Take some time with it because it's kind of it's the beginning. As I said, there's this whole thing in math called category theory, and it's all about how you take a certain discipline in mathematics, like group theory or ring theory or topological space or measurable spaces or whatever, and the objects are those things like groups, and there are morphisms between them, which in this case would be homomorphisms. So you study the relationships between these different objects. It gives you some understanding of what you're doing. Deep stuff.
For the homework, I'll
look again.
I had too many homework.
It looked great.
tabs.
It was special relativity or something.
Yeah,
it looks fantastic.
Because I turned it in before, and then I waited till the last second to turn in my physics homework, and I actually turned it again to this class. And so it covered it up, and I thought I left you a comment. I don't know if you can see those.
I'll look, and if I can't find it, I'll change the grade, of course. I just thought I'd put a 0 there for now, so I would remember to deal with that.
Yeah, I was just like, I'm pretty sure I turned it in.
Yeah, I'll double check.
All right. And you're out there for 3:30.
3:30.